Welcome to my YouTube channel. In this video, I am going to explain you how to calculate seismic load based upon European standard. In the right hand side, you can see European standard code EN 1998 of part 1, which we are going to use to calculate seismic load based upon European standard. In the left hand side, you can see it is a Excel sheet developed to demonstrate to you about the seismic load calculation. Generally, these European standards, which are developed by various nations of various members in European nations. So this code is applicable for most of the European nations, such as Austria, Belgium, Cyprus, Czech Republic, Denmark, Estonia, Finland, France, Germany, Greece, Hungary, Iceland, Ireland, Italy, Latvia, Lithuania, Luxembourg, Malta, Netherlands, Norway, Poland, Portugal, Slovakia, Slovenia, Spain, Sweden, Switzerland, and UK. This European standard generally we used to call it short form as CEN, CEN or EN. EN is nothing but it is a European denormalization. CEN means Committee European Denormalization. So this code EN 1998 part 1 is Eurocode 8 design of structures for earthquake resistant part 1 general rules seismic actions and rules for buildings. So this will support us to calculate seismic load. So first we need the input as a seismic coefficient AG. Generally this to be provided by the project owner, or this should be available in project technical specification. So here I am considering 0.3 for our calculation purpose. Ground types, this should be referred as per table 3.1. For that we need to go page number 34. So this table 3.1 give you 7 ground types. The first ground type A means the description states that a rock or other rock-like geological formation including at most 5 meter of weaker material at the surface. Next ground type B states that deposits of very dense sand, gravel or very stiff clay at least several tens of meters in thickness characterized by a gradual increase of mechanical properties with depth, and C ground type stating that deep deposits of dense or medium dense sand, gravel or stiff clay with thickness from several tens to many hundreds of meters. D means a deposit of loose to medium cohesion soil. E is a soil profile consisting of a surface alluvial layer with Vs values of type C or D and thickness varying between about 5 meter and 20 meter, underlined by stiffer material with Vs greater than 800 meter per second, and S1, S2 are deposit of layer containing layer at least 10 thick of soft clay sills with high plasticity index, and deposit of liquefiable soils of sensitive clays or any other soil profile not included in types A to E or S1 respectively. So I had selected C from the drop down list, whereas this drop down list will provide the definition and description of stratigraphic profile based upon the EN 1998 part 1. So C, let we consider C as a ground types for this calculation purpose. Next input required is important class of building. This we need to refer as per table 4.3, page number 53 to be referred for this. So this table shows you important classes of buildings. There are 4 classes. The first important classes defines buildings of minor importance for public safety, example agriculture or building, etc. Agricultural building, etc. And second one is ordinary buildings not belonging in the other categories. Three class. The third class is Buildings, those seismic resistant is of importance in view of the consequences associated with a collapse. Example, schools, assembly halls, cultural institutions, etc. And four importance classes, buildings whose integrity during earthquake is of vital importance of civil protection. Example, hospitals, fire stations, power plants, etc. Also, there are some notes is given here in important class 1, 2, and 3 or 4 correspond roughly to consequence classes CC1, CC2, and CC3 respectively, defined in 1990-2002 Annex B. These important classes factor generally why we want to refer is we need to know that what is the load combination factor if this seismic is going to come along with the other loads such as a dead load, live load, or even some part of wind load. If it is considered means how much percentage and what is the load factor. So for that we need to understand the importance of a class of for building. So I am selecting here class 3, which is a building whose resistant is of importance in view of the consequences associated with the collapse. For example, schools, assembly halls, or cultural institutions, etc. So likewise, we can also select based upon the table 4.3. So then the next requirement is important factor as per table 4.3. So in the point number 5p, the gamma 1, that is important factor as per the class 2 is mentioned as 1, and for importance factor for other classes such as 1, 3, and 4, it is mentioned as 0 0.8, 1.2, and 1.4 respectively. So for our class 3 of importance of building, I am having a value of 1.2. So the 1.2 I had bring to this value from a backup table which was created in line with the tables in the European National Standard EN 1998 Part 1. Next one is behavioral factor Q. For this we need to refer table 5.1. So page number 82, we have to look into that. Here is the table 5.1. There are four structural type is defined here. First one is a frame system, dual system, collapsed wall system. For that, for DCM value is 3 times alpha 0 divided by alpha 1, and for DCH it is 4.5 alpha 0 divided by alpha 1. For uncoupled wall system it is 3. For DCH it is 4 into alpha 0 divided by alpha 1. Next one is the torsionally flexible system. For that DCM is 2, DCH is 3. Inverted pendulum system DCM is 1.5 and DCH is 2. Here DCM, DCH is nothing. It is nothing but it is a ductile class to be referred for the structure. If the structure is designed to capable to hold the seismic forces, if it is built with ductility, so based upon that category, whether either it is a low or medium or high, so that ductility category is defined as DCM, DCH, and DCL. For ductile category, we need to refer page number 137. So here in this table 6.1, well, it is explained. If the structure is a subject to low dissipative structural behavior, then that structural ductility class to be considered as a DCL, that is a ductility class low. And for a dissipative structural behavior, if it is having limited or some extreme, somewhat below extreme dissipation ductility requirement, for that we need to consider DCM, that is a ductile class medium. If the building structure is highly designed to have good ductile uh, capability, then that should be comes under DCH, that is ductile class high. So thus we need to consider that behavioral factor Q with respect to the ductility class. So let me come back to the same page of table 5.1. So here for our calculation purpose, I had considered a torsionally flexible system which is having a high ductile class. So the factor should be 3. So I am entering the value 3 here. Next one is type of elastic response spectrum curve. Generally, the selection of this type of elastical response spectrum curve is depends upon the customer requirement, or even the designer can select which elastic response spectrum is applicable for his design. There are two elastic response spectrum curve, S1 and S2. There won't be any much bigger difference by selecting this. Only some 4% of difference might be there while finding the base shear of seismic. So S2 is having more critical value of seismic base shear compared to S1. So I am choosing the S2 for my critical design criteria. So for S2, we need the inputs like soil factor, lower limit the period of constant spectral acceleration, upper limit period of constant spectral acceleration, beginning period of constant displacement, such as S, TB, TC and TD respectively. So for that I need to refer figure 3, which is available in page number 39. So these are the two chart, type 1 and type 2. So I am selecting, I am having as a drop down list here S1 and S2, which is equal to type 1 and type 2 elastic response spectrum chart respectively. So if you consider here, if you see here, so this chart I had extracted the values and added into that backup table for elastic type 1 and 2, so that this value S, TB, TC, TD will come directly from this table by selecting simply this drop down list. We no need to refer the chart or the standard reference for the each and individual calculations. So for elastic response spectra curve S2, I am getting S value as 1.5, TB value as 0.1 second, TC value as 0.25 second, TD is 1.2 second. So here are the table 3.3 and 3.2. So from this we can able to extract the values based upon the ground type and the type of elastic response spectra curve. So next one is a total height of structure. This is an assumed value. I had assumed 10 meter for our calculation purpose, and fundamental period of vibration we need to refer class 4.3.3.2, page number 57. So here is for building with the heights up to 40 meter, the value of T1 in second may be approximately by the following expression: T1 equal to Ct into h power 3 by 4. So here Ct value also we can consider 0.085 for moment resisting space steel and 0.075 for moment resisting space concrete frames, and for eccentrically braced steel frames 0.05 for all other structures. So we don't know what kind of structures we are going to design, as this is a calculation for a sample. So I am considering the last category, that is 0.50. For this case, like for all non-moment resistant structures, So it is 0.05. So I so then I am also having the value of height. So it is easy for me to calculate fundamental period of vibration. So for me the fundamental period of vibration T1 is coming 0.28 second. Next one is correlation factor. For that we need to refer class 4.3.3.2.2, page number same 57. Here it is lambda is the correlation factor. So here the lambda is a correlation factor, the value of which is equal to lambda equal to 0.85 if T1 is less than or equal to 2 times Tc. So our case, if we see our T1 is 0.28 and Tc is 0.25. So 2 times Tc will be 0.5 second. Our T1 is 0.28 which is less than 0.5, that is 2 times Tc. So hence we need to consider 0.85. For other cases we can consider the lambda as 1. So this is what defined here for correction factor. Next one is ordinate factor. For that we need to refer class 3.2.2.5, page number 56. Yes, page number 57. Here it is. St of T1 is the ordinate of the design spectrum. For that again we need to refer class 3.2.2.5, so page number 42 to be referred. So there are 4 formulas to calculate ordinate factor St of T. So in the first case, in case our fundamental period of vibration T1 is greater than 0 and less than or equal to TB, then we need to consider ordinate factor of a spectrum, uh, ordinate factor of design spectrum as per this formula: Ag into S 2 by 3 plus T by TB into 2.5 divided by Q minus 2 by 3. In the next case, if TB is less than or equal to T and less than or equal to TC, then we need to consider this formula: St of T equal to Ag into S into 2.5 divided by Q. The third case is Tc is less than or equal to T and less than or equal to Td, then we need to consider ordinate factor as St of T equal to Ag into S into 2.5 divided by Q into Tc by T. Then last condition is if Td is less than or equal to T, then St of Td equal to Ag into S into 2.5 divided by Q into Tc into Td divided by T square. Our case, if we look into our calculation, so our calculation, if you see, the Tc we are having 0.25 second, whereas T is 0.28 second. So in this case our T1 is greater than Tc. If you look into that TB, which is 0.1, so our T1 is greater than TB. But, so this case is not applicable because Tc, our case, our T1 is greater than Tc, so this case is not applicable. Whereas our T is not less than TB, so this case also not applicable. And finally, the third case, if you see, Tc is less than or equal to T. So this is satisfied in our case, and T is less than or equal to T. Here our Td is 1.2 second, our T1 is 0.28 second. So this third case is applicable for our formula to calculate ordinate factor. And finally the TD, if in case TD is less than or equal to T, our case it is not applicable this fourth formula also. So we are considering the equation the 3.15 ordinate, hence ordinate of the design spectrum is AG into S into 2.5 divided by Q into TC divided by TD. So here the formula which I am having is inbuilt with all the four cases. So this will check and uh, extract the required values from the above input. So finally I am getting the ST of T1 value as 0.34. Then the next one is a total vertical load. This to be as per the structure model and the technical specification requirement. Generally, that total self weight we need to consider for seismic load calculation. The seismic mass to be considered as a self weight or total weight of the structures which are incorporated with all the imposed load. Addition to that, in some of the technical specification or the project owner, they request the require to include the live load of some part of live load. I can say 20% or 50% or some 60% of live load to be considered along with or additional to the structural self weight and structural and non-structural element of any building. So likewise, that total vertical load we need to consider for our calculation purpose. But in this sample calculation, I am considering 10 kilonewton. I am just actually this is a tentative value, 10 kilonewton. Then finally we are in last line item, base shear force FB. So for that we need to refer class 4.3.3.2.2, page number 56 and 57. So here is the base shear force. So the formula to calculate the base shear force Fp equal to St of T1 into M into lambda. So here St into T1 is the ordinate factor which we had just calculated as 0.34. Next one is M. So T1 is a fundamental period. We had calculated already 0.28 second. Next one is mass. Is the total mass of the building. Ours is a 10 kilonewton, which is a assumed, which is an assumed value. And the next one is lambda. Lambda is a correction factor we already calculated as 0.85. So applying all these calculated values in the formula for Fp, I am getting 2.89 kilonewton as base shear force. So this 2.89 is roughly 30% of total vertical load. So with this, I am with this topic is over. So our ultimate aim to calculate base shear force is done. That's all about this topic. Look description for more related videos. Thank you.